Hello, welcome to my channel. This is an educational channel where we review and study up on all kinds of different theories, mostly theories of everything, all-encompassing theories that can have a massive impact on your understanding if you tune in and are diligent. Usually these theories are a little bit difficult. You have to apply yourself, but the payoff is great. So today, as we have for the previous 204 videos, we're looking at the reciprocal system of theory of Dewey B. Larson. And Mr. Larson died back in 1990, but for the 60 years before that, he was developing the reciprocal system. And the basic idea is that we live in a universe of motion. Not a universe of matter, not a universe of energy, but a universe of motion. And motion is the relationship between space and time. Motion is basically a fraction that has space or time as the numerator and time or space as the denominator. Space and time, however, can come in 3 or more dimensions. That is what Larson calls coordinate space and coordinate time. And then space and time also have their scalar aspect or their clock aspect. Larson calls it clock time and clock space. Space is, time is always flowing, progressing. It's always getting later and later and later, but in no particular direction. That is a scalar motion, a motion that has a magnitude but no direction. In the same way, there is clock space. Space is always getting farther and farther and farther apart, but in no particular direction, which was actually observed by the Hubble telescope that determined that all of the distant galaxies are moving away from each other. And that goes way back to the 1920s, I believe. And then space and time also come in only discrete units. There is no continuity. Space and time come in small chunks. And one chunk of space in one chunk of time is the speed of light. So the speed of light is 1. Basically, that means that the speed of light is a midpoint. Unlike legacy science, where 0 would be the midpoint, and you would have plus or minus, in the reciprocal system, we're dealing with multiplicative inverses, and so 1 is at the center, and then greater than 1 would be 2, 3, 4, 5, 6, and less than 1 would be 1/2, 1/3, 1/4, 1/5, 1/6. So it's when you multiply them, you get to 1. Not when you add them, you get to 1. Okay, and then we are looking at Larson's book called Nothing But Motion, and this is a book that's primarily on atomic physics. We are in the midst of a pretty difficult chapter here called Cosmic Ray Decay. Cosmic ray is a cosmic atom. Now, when you have this speed of light as the midpoint of the universe, or the null point, or the origin, or the ether, or the neutral point of the universe, then you have 2 separate sectors of the universe. The material sector, which we're familiar with, where we have coordinate space and clock time. And then we have the cosmic sector, where everything is moving faster than the speed of light. In the material sector, everything is moving slower than the speed of light. In the cosmic sector, everything is moving faster than the speed of light, and we have coordinate time and clock space. And The rules are the same in both, and you can actually extrapolate one to the other by simply inverting the roles of space and time. Now, so that's where you get cosmic atoms. You have material atoms, which are combinations of motions. An atom is really a combination of two or three different rotations that is built upon a photon, which is a simple harmonic motion or a wave, which is in itself a combination of two motions. So now what happens with we would not be able to really observe any type of cosmic ray or any type of cosmic atom until it starts impinging upon the material sector. So and this happens also in the reverse order of material atoms going over to the cosmic sector. That happens when a star or a galaxy explodes, and the explosion goes beyond the speed of light, a powerful explosion. And when that happens, the atom is thrust into the other sector because it crosses the speed of light boundary, which is the one, the boundary between the two sectors. And so when it crosses over, it becomes unstable, radioactive, because it is not built for that environment. It has, your various rotations and vibrations, and those are not stable in that environment. And in the same way, when a cosmic star or a cosmic galaxy explodes and moves moves everything past the speed of light boundary, then it moves into the material sector. And then we're able to begin to observe it. And so this is what Larson is talking about when the with cosmic rays. Cosmic rays come across the material sector to the material sector, and they immediately begin to decay, or they're unstable and they're radioactive, and they change into more stable configurations. And in the case of cosmic rays, they actually change a number of different times into different cosmic atoms until they actually decay into a material atom, or two material particles, actually, that are massless neutrons. So it's primarily cosmic hydrogen and cosmic helium that come into the material sector, and they gradually or quickly decay up the cosmic periodic table until they get to cosmic krypton. And then at cosmic krypton, it flips, and they turn into two massless neutrons. Larson goes through this earlier in this chapter. Right now, and so these are what legacy science calls the mesons, and in particular the piperons. Now, when you look at Larson's system, he basically develops his system through theory only. So he has two fundamental postulates. We went through the main one of those, that has, the universe is made out of motion. Motion is the relationship between space and time. Space and time have their coordinate and their clock aspects, and they come in only discrete units. The other postulate is mostly having to do with math and geometry. And then he takes those postulates and he derives or deduces a theoretical universe, and then he compares his universe with the universe that the scientists have observed and measured. So his deductions do not come with labels, and so it's just okay, something like this, something that fits this description exists. It's up to matching that function with a label that the scientists have already arrived at, if any. And in this case, Larson's cosmic atoms coming into the material sector matches with what the scientists call mesons. And okay, so we will take over here where he's talking primarily about the pion, which is, I think, cosmic silicon 27. No, let's see. Yeah, I think that's right. Okay. Pions are frequently reported as products of observed cosmic ray events initiated by primaries. As we will see in the next chapter, such production is quite feasible where there is a violent contact of some kind with the release of a large amount of energy. But direct production of pions in decay is not consistent with the decay pattern as derived from theory. The apparent direct production is, however, understandable when the relative lifetimes of the pion and the earlier decay products are taken into consideration. There is no reason to believe that normal decay in flight will result in any change of direction. Ejection of massless particles will take care of the conservation requirements without the necessity of directional modification. Because the entire decay process up to the production of the pion occupies only a very short time compared to the entire lifetime of the pion itself, it is unlikely that the usual methods of observation will be able to distinguish between a pion and a cosmic particle undergoing a complete decay to the pion status in flight. In the kind of a situation mentioned in chapter 14, for instance, where a pion apparently leaves the scene of an event in a continuation of the direction of motion of the primary and carries the bulk of the original energy, leading to the conclusion that the primary decayed directly to the pion, there is nothing in the observations that is inconsistent with the theoretical conclusion that during a short interval at the beginning of the motion attributed to the pion, the cosmic particle was actually going through the preceding steps in the decay sequence. The next event in this decay sequence, the decay of the pion, involves an 8-unit increment to C argon 35. Again, the zero isotope is the stable form. This leads to a mass of 106.42 mega electron volts and a theoretical life equal to that of the pion. The observed particle is the muon with mass of 105.66 mega electron volts formed by decay of the pion as required of the theory. Both the decay to cosmic silicon 27, the pion, and the subsequent decay to C argon 35, the muon, continue the same pattern of a uniform 1-unit increase in the cosmic mass increment in each succeeding event that was followed in the earlier decay steps. But inasmuch as C argon is equivalent to helium, that's where you flip one to get the other, using 4 as the basis of a two-dimensional rotation. And so since C argon is equal to is notated by Larson as cosmic 320, its inverse then would be 210, which is helium, which from the material standpoint is only one step away from the neutron that is the end product of the decay process. The following ejection of positive displacement carries the cosmic atom to the final cosmic structure, C krypton. Each of the two rotating systems of the C krypton atom is rotationally equivalent to a neutron and converts to that particle. Since C krypton is massless, that is, its observed mass is merely the mass equivalent of the inverse mass of the cosmic sector, the conversion products are massless neutrons or their equivalents, pairs of neutrinos and positrons. Some of the aspects of this conversion process will be given further consideration in Chapter 17. Unlike the decay events which involve changes in the atomic structure and therefore do not take place until they must, the conversion of the C krypton rotations to massless neutrons is merely a change in scalar direction to conform with the new environment, and it takes place as soon as it can do so. Consequently, the C krypton atom as such has a zero lifetime. As soon as the particle ejection from C argon takes place, the conversion to massless neutrons begins. In view of the non-appearance of C krypton, the apparent lifetime of C argon, the muon, is the sum of its own proper lifetime and the conversion time. The value reported from observation is 2.2 times 10 to the minus 6 seconds. A theoretical explanation of this value is not yet available, but it is probably significant that the difference between this and the life of an uncharged particle moving in one dimension, about 10 to the minus 8 seconds, is approximately that associated with a gravitational charge. The absence of the C krypton atom from the decay process is not due to any abnormal instability of this cosmic atom itself, but to the preference for the alternate scalar direction that prevails in the material environment. In the reverse process, the directional preference favors the C krypton atom over the neutron alternate. It plays a prominent part, as we will see in Chapter 16. In those cases where the incoming cosmic atom is not in the normal decay sequence, it ejects enough positive displacement in one or two decay events to reach one of the positions in that sequence, after which it follows the normal path in the same manner as the products of the decay of cosmic hydrogen. However, these heavier elements are beyond the stability limit for two gravitational charges in a low energy environment, and consequently they do not form structures analogous to the psi particles, psi particles. This has the effect of increasing the probability that some of the decay products that normally carry one gravitational charge will occasionally be found in the uncharged condition. The one allowable charge would result in an asymmetrical structure during the time that the speed of these particles is in the two-dimensional range, and if they are observed at this stage, they are likely to be uncharged gravitationally. The uncharged lifetime for a particle moving two-dimensionally is approximately 1 natural unit of time, or about 10 to the minus 16 seconds. Such a life is the most definite indication that an observed particle is in this early stage of the decay process. For example, the eta particle with the observed mass of 549 megaelectron volts and a life of 0.25 times 10 to the minus 16 seconds is probably a gravitationally charged C beryllium-7 atom, which theoretically has a mass of 532 megaelectron volts. A more questionable identification equates the Rho particle, RHO, with C lithium-5. The theoretical mass in this case is 745 mega electron volts, and the observed values range from 750 to 770, the more recent measurements being the higher. The Rho lifetime has been reported as about 10 to the minus 23 seconds, but this is too short to be a decay time. It is evidently a fragmentation time, a concept which will be explained in connection with the discussion of particle production in the accelerators. Both C lithium 5 and C beryllium 7 are in the normal decay sequence, a fact which lends some support to the foregoing identifications. The reported observations of particles that are outside the normal decay sequence will be given some further consideration in the next chapter. If the incoming cosmic atom is above C krypton in the cosmic atomic series, so that it cannot enter the normal decay sequence in the manner of the elements of lower atomic number, it must nevertheless separate into parts at the end of the appropriate unit of time. And since it cannot eject massless neutrons as the lighter atoms do, it fragments into smaller units, which then follow the normal decay path. All right, well, that is the end of chapter 15. If you understood any of that, pat yourself on the back. If not, just listen to me going over the chapter over and over again. It's probably the last 6 videos, but I would recommend going back to the start and going through all of it, because Larson introduces new terminology. I can only imagine how he wrote these chapters. It must have taken him forever to write these chapters. They have all the information in them, and they are, I think, well written, but he's using so many difficult terms that he only knows the meaning of, so it's difficult. But hang in there, and we'll come back tomorrow and go through chapter 16, which is called Cosmic Atom Building.